Today we are explaining the paper training AI scientists to replicate research.
What problem is this paper trying to solve?
The paper starts from a basic requirement of science. When someone repeats an experiment, the results should be consistent enough to support or falsify the original explanation. But machine learning has a replication crisis, and an AI agent cannot simply copy a paper because the paper leaves out many decisions that were made during the research.
Why do existing AI scientist systems struggle with that kind of task?
Earlier systems often rely on a fixed benchmark and a reward that can be checked automatically. That works for a narrowly defined challenge, but it can make the agent learn an adaptation to that benchmark rather than a transferable research skill. Hand-designed benchmarks also take substantial human labor. On the other side, an LLM judge that imitates peer review faces the opposite problem. The setting is so open-ended that the score becomes noisy and difficult to calibrate.
So what does this paper make concrete enough to train on?
It introduces Replica, a scalable task space for paper replication. Replica contains 240 training tasks and 68 held-out test tasks, drawn from 100 machine learning and AI for science papers. Each task asks an agent to reproduce one results figure while giving it the paper with that figure removed. A 60-minute limit, and 1/7 of an H200 GPU.
How can a benchmark like that be generated without handwriting every task?
The pipeline scans a paper for main text results, plots, and captions, localizes each plot with a verifier loop, and irreversibly read exit from the PDF. The task is then the caption, the hidden original plot. The authors inspect the generated tasks and remove cases where the plot was not actually a result or the redaction was poor. A paper contributes between 1 and 13 tasks.
What happens after the redacted tasks are ready?
The agent trained on these tasks is Faraday. It is a 27 billion parameter outer model that uses Codec's GPT 5.5 as a coding agent tool. The outer model decides what to investigate and how to spend the budget, while the coding agent edits files, runs experiments, and produces plots. The harness stays simple: a container, a linear history, internet access, and 5 basic tools for reading, searching, patching, listing files, and running shell commands.
A visual match alone could reward a shortcut. How does the judge tell a faithful replication from a copied-looking plot?
The paper uses a task-specific rubric rather than a single generic prompt. Cloudopus 4.7 generates the rubric from the paper while hiding the original plot, so the rubric focuses on the scientific claim instead of exact axis ranges or formatting. It scores 5 dimensions: visual similarity, support for the claim, whether the experiment implements the described method, use of the limited compute budget, and scientific integrity.
How does that score become a stable training signal over a long experiment?
Codec's GPT 5.5 evaluates the rollout with access to the code, the interaction trace. It can inspect or rerun the generated work before assigning scores from 0 to 1. During training, the authors sample the judge 3 times to reduce noise, average the results, and ask for credit weights for individual turns. Those weights are used in a modified GARPO update, so useful decisions earlier in a long rollout can receive credit.
Before trusting that reward for training, did the authors check whether it agrees with people?
Yes, experts rank the same rollouts, and the rubric judge agreed with human rankings better than a constant baseline prompt. Independent samples of the rubric judge had a Kendall TAU agreement of 0.66, compared with 0.46 for the baseline judge and 0.30 between humans. Agreement with humans was 0.19 for the rubric judge versus 0.15 for the baseline. The rubric judge was also less noisy.
What does Faraday achieve when it faces the actual replication tasks?
All agents receive the same paper, the same 60-minute single GPU budget, and data valuation rollouts per task. Faraday outperforms Claude and Codex on 73% of in-distribution machine learning tasks and on 60% of held-out AI for science tasks. On the test split, its average score is 6% higher than Claude and 8% higher than Codex. The whole score distribution shifts upward, including a thinner tail of weak attempts.
Is that improvement really learned behavior, or could a better prompt have produced the same result?
They tested that alternative by automatically optimizing the Codex prompt for 24 generations, using rollout histories and judge feedback. The optimized prompt identified some failure modes, but it did not meaningfully improve the original Codex baseline. The gap to Faraday remained, which suggests that post-training changed the agent's policy for research decisions rather than merely adding advice to the prompt.
Does the learned behavior transfer when the task changes the data or the claim?
The authors create 20 counterfactual tasks from 10 papers. One variant keeps the claim but swaps the dataset or environment, and the other changes the claim in the same setting. Faraday's rollouts beat Codex on 19 of the 20 tasks according to the rubric judge. That is evidence for a bridge from replication toward innovation. But the authors also note an important caveat. The judge itself was not validated on these imagined tasks.
Are the gains consistent across the kinds of papers and topics in the benchmark?
The difficulty is not uniform. More recent papers are harder for every agent, likely because their details are less represented in pre-training and their experiments use more compute. AI for science papers are also generally harder than machine learning papers. Even so, Faraday leads across every research topic shown in the analysis, indicating that the learned behavior is not tied to one specialized subject.
The scores show who wins, but what does Faraday do differently inside a rollout?
The qualitative analysis finds two recurring differences. Faraday implements the mechanism that the experiment was designed to test, while a baseline sometimes hardcodes the expected output or replaces the method with an oversimplified shortcut. Faraday also reproduces more of the original experimental scope without dropping important pieces just to get a favorable plot. In its strongest rollouts, useful insights accumulate even though the agent has no special evolutionary harness and cannot see the judge's reward during evaluation.
Did human experts see the same difference, and what limits the conclusion?
In a focus study of 41 rollouts selected because Faraday had a large judge advantage, humans preferred Faraday over both Claude and Codex in 29 cases, significantly more often than chance. But this was not a random sample of all tasks. The paper also reports failures where a faithful original result was not reproduced and warns that those failures do not imply a flaw in the original research.
What are the main limitations before we call this a general scientific researcher?
The experiments are deliberately small. Training uses 60-minute tasks, unlimited GPU access, while the larger resource check covers only 8 tasks. Faraday beats Claude on average and on 5 of those 8 scaled-up tasks. But stronger validation needs more tasks and the judge validated at that scale. The imagined innovation judge is also unvalidated, and the safety scope is limited to in silico work with no physical laboratory access.
Then what is the paper's strongest overall claim?
The paper's claim is not that Faraday has solved scientific discovery. It is that a small outer model can learn research judgment from a scalable replication curriculum, use a coding agent as an execution tool, and improve faithful experimental work beyond the frontier model acting alone. Replica turns replication into a grounded but underspecified training problem, and the results suggest that mastering those decisions can be a first step toward agents that handle longer horizon scientific work. That is the key idea: train scientific judgment on replication first, then test whether it transfers to harder research. Thanks for watching.